can change its form. The next one, which has a little bit of bearing on biology, is the fact that the entropy, E-N-T-R-O-P-Y, of the universe is increasing. Does anybody know what entropy is? Some of you said chemistry or physics before.
It's like the decay of a higher energy state or system into that of a lower energy
Sure.
state or system.
Entropy is the amount of disorder. So if we say the entropy of the universe is increasing, we're saying the universe is becoming more and more and more disordered. Which makes sense. Was there a time when the universe was perfectly ordered? Yes, right at the very beginning. When all of the matter and all of the energy that ever existed was at one finite point. It's as organized as you can get. Well, at one point, that nicely ordered system blew up and has been moving out in all directions ever since. Near as we can tell, somewhere about 12 or 13 billion years ago. And as the universe continues to spread out, it's becoming more and more disordered. Things are getting farther and farther away from each other. We call that disorder. Now, how does that relate to biology for living things? Is entropy a constant? Is everything always falling apart? No. But what does it take to keep it together?
Lots of energy.
It needs energy. You do that. I'm assuming at some point you'll go home tonight and you'll eat. You're going to eat to avoid falling apart. But in the end, entropy always wins. Because we don't like to think about it, but eventually what's going to happen to all of us?
You'll die.
We're going to die, they're going to stick us in a box, chuck us in the ground, and we'll fall apart. That's okay, that stuff will be released back into the environment. Other things will suck those nutrients out of the ground, and you'll be part of something else. Everything we've ever had, remember we talked about this last week, everything we've ever had is everything we have. For all you know, that soda or that water or that coffee you're drinking now could have been dinosaur urine a couple million years ago. Just gets recycled, the same stuff. But that entropy is increasing. It's happening all the time. We'll spend our life fighting it, trying to stay together. If you look at, for example, a human being, pretty complex system, pretty well organized and put together, pretty sophisticated. But it takes a huge amount of energy to make that happen. On average, 2,000 kilocalories a day just to maintain. You eat more than 2,000 kilocalories a day, well then you add a little. You decide you want to lose a little and you eat less than that, then you'll lose weight. But still, that's a fair amount of energy. And the last one is purely a physics chemistry thing, has nothing to do with bio, but I can tell you about it anyway. And the third one is that absolute zero can never be reached. Absolute zero is a matter of motion. Everything is moving. Believe it or not, your desk is moving as you sit at it. Not very much. The atoms are resonating inside, so I call it a solid. There's not a lot of space between them, and they're resonating fairly tightly, so you can put things on it. But if we get to absolute zero is the absence of movement, the absence of heat, then even the resonance of those atoms
Can never
stop.
be reached.
And the reason we can never reach there has to do with physics. If you want something cold, where do you put it? You put it in the fridge. Why does putting in the fridge, we don't think about this because we do it all the time, but why does putting something in the fridge make it cold? True. But what is true of your refrigerator that's different than whatever it is that you want to cool down?
Your refrigerant is the energy to make it cold.
Refrigerator is colder, right? Things cool down by putting them in an environment that's cooler than they are. So why can we never get to absolute zero? Follow the logic of that through.
You don't have anything that's less than absolute zero to put it in?
Right, you'd have to put it in somewhere that would be less than absolute zero, but absolute zero is as far as you can go, so you can't be less, so we can't get there. We've gotten close, we've got within, a fraction of a degree. I think the closest we've got to so far is 0.25 Kelvin, which is the measurement of absolute zero. But that's about it. Absolute zero is pretty cold. Because absolute zero is actually, if you look at the freezing point of water, water freezes at 273 degrees Kelvin. So that gives you a concept of how cold it is. All right, that's enough physics. Now we can go back to biology. The main energy molecule in living systems is ATP. ATP is good enough. It's short for adenosine triphosphate. It's like a biological battery.
What was that, the main?
The main